All right, it is 9 o'clock, and as usual, try to start on time. So what we'll do today is to continue our discussion from Tuesday. On Tuesday, we kind of talked about how to use two N-type transistors and two P-type transistors to create a NAND gate. And what we'll do today is to look at how do we use multiple NAND gates to create gates that we are more familiar with, meaning we have NOT gates, AND gates, and NOR and OR gates. So we'll start with that, and then I think we're going to have enough time to talk about base conversion as well in today's lecture. So that's kind of the scope of today's class. I am working on uploading the lecture recording on Tuesday onto the GPTTA. So it serves multiple purposes. It's mostly for selfish reasons, because if I do it this way and I clearly indicate the date and maintain the timestamps, I can actually ask the TA, when did I talk about this concept? Okay, so obviously that is useful for you as well, because if you want to say, okay, I want to revisit a certain lecture content, like, okay, I want to go back to when TAC talked about, how to make an AND gate or NAND gate, you can now, use the TA as a tool to help you locate the exact date and time so that you can revisit that segment if you want to. All right. So it's brewing on this side, that you cannot see, but I'll finish that, when I have time, probably during your lab. All right. So I do want to point out what you're supposed to be reading, and it is this particular module. Okay. So this module is 0281. So when you refer to the module, this is the module name, and you can also create your own little catalog of which module talks about what. So right now we are getting to this point here. NAND gate is all we need, which essentially is saying that a NAND gate is a universal gate, meaning that you can use multiple NAND gates to create a NOT gate, an AND gate, or OR gate. So the concept of a gate in this class, which is hardware based, versus operators that you have learned in CISP 360, they're closely related. Okay, the only difference is, oh, we are talking about hardware in this class when we use the term gate, and we are using operator to describe ampersand ampersand, vertical bar, and the exclamation point operator when you're writing CISP, I mean C++ code. So that's the only difference. But they are really kind of the same thing, except one is hardware, one is in text representation. So without using any additional time, we are going to kind of dive right into how to do just that. So a quick review, okay? What exactly is X NAND Y? Okay. In other words, if I were to use C++ operators, what would this look like? So you have to remember what is NAND. So what exactly is NAND? Why is it spelled as NAND? Not AND. It is the negation of AND. Okay. So if you are, I know you guys are most of you are shy because there are more introverted people in computer science than most of the other disciplines. So I know some people are shy. So if you're thinking the same answer in your head, congratulations. Okay, you're retaining what you should be learning. On the other hand, if your mind is kind of blank, is drawing a blank, then maybe it's time for you to consider, spending some time to review the material before class and also after class. So you're supposed to spend some time after class on Tuesday to review the material that you have just learned, and if possible, spend some time before today's class just to review. Okay, these are the quick things, just a quick review. These are the things that I have learned from the previous class, because that will help you reestablish the context to so that this class becomes more effective. All right, so this is essentially X ampersand ampersand Y, but with the negation on the outside. So now let me ask you what is going to happen with this. Okay, so what do you think this is equivalent to? Now, if you say, I have no idea what it is equivalent to, then the next question is, can you figure out what it is going to do? So based on what you have learned in CISP 360 already, can you figure out what this new expression on the third line is going to do? The first question is, from the perspective of Boolean values, how many values do you think x can possibly be? Two. Very good. Okay, because it's a Boolean, so that means it can either be true or false. Okay, so that means there are only two test cases here. Let me draw up a truth table. This is the value of x, and this is the value of the negation of x and x. X can be false, x can be true. So now the question really is, if x is false, what is the negation of x and x? It's going to be true. Okay, very good. And when x is true, what is the outcome of the negation of x and x? It's going to be false. Very good. So now we look at this and go like, hey, that resembles something that I already know, which is just the negation of x. Because the negation of x when x is false is true, and the negation of x when x is true is false. So are we understanding this table, how it is supposed to be read, and why it is here? All right. So this established the equivalency. It tells me that the negation of x and x is really the same thing as just not x. But the negation of x and x is also known as x NAND x. So now we have just figured out how to use a single NAND gate to implement negation, simple negation. Is that okay? Yes. Yes, there are simpler circuits to do it. The reason why we want to use NAND gates to impersonate all the other gates is because we have devices called FPGAs. So FPGAs stand for F is field, P is programmable, G is gate, and A is array. So FPGA is field programmable gate array. Why is that important? Okay. Well, you can do a Google search or an AI search and ask, why is FPGA an important device? But I'll give you the answer too. So imagine you are making the next generation of cell phones, okay? And there are many things will happen within the next 2 years or so before the hardware is obsoleted. Well, this is an older phone than 2 years, okay? But most people only keep their phones for about 2 to 3 years, and then because of obsolescence, the battery cannot hold a charge anymore, and various other reasons, people just want to upgrade. So 2 years. But within those 2 years, there may be some really nice, cool ways to say do voice compression. Okay, so you can have high fidelity voice when you're talking on the phone without using a lot of cell phone bandwidth. Or there may be better ways to do AI stuff. Okay, so maybe you can move down, maybe you can offload some of the cloud-based AI computation onto your phone because somebody discovered a really great way to do it. So there's no way you can anticipate what kind of specialized hardware you should be putting into the cell phone today because nobody has a crystal ball for the next 2 years. Is that okay? So let's just say that somebody discovered, oh, I found a really, really fast way to do voice compression. I mentioned that before. And so how are we going to implement the new voice compression algorithm or method on the phone when the hardware is already set? Well, I think asking your consumers to take the phone apart, desolder a chip, and then resolder a chip is out of the question. I cannot even do that, okay? Because the density of the chips these days is to the point where, I mean, it's really hard for an individual with just standard tools to do it. So FPGA is field programmable, which means you can change the programming of a FPGA on the fly without even rebooting the phone, without even going like, oh, I'm reflashing something and then wait for a long time and then reboot the phone. You can update it on the fly because it's RAM based. It is not flash based. So that's field programmable. Gate array is simply saying that it is a massive number of universal gates. So there are two types of universal gates. NAND is one, NOR is the other one. So we'll focus on NAND. So what FPGAs do is it allows you to specify the routing between the NAND gates. So you can now say, oh, the output of this NAND gate goes to the input, the first input of that NAND gate, and then the output of the other NAND gate goes to the other input of this NAND gate, and so on. So you have the flexibility, you can control the routing between the connectivity, between the connections of these NAND gates. So as a result, you can now basically create a new quote unquote specialized hardware for certain types of computation as a co-processor for your phone. And it can be programmable, it can be updated over the lifespan of the entire phone. So that's already happening. You know, a lot of cell phones actually have FPGAs in it, you know, in order to do some of the specialized, processing. It wasn't feasible before because FPGAs used to be very expensive. And these days, because of semiconductors getting more and more efficient, or we are reducing the size and we have better technology, so FPGAs become viable to become a part of a cell phone. So getting back to NAND gates, why it is important to do this, that is why. So now the next one is what about just regular AND? Okay, so now we want to do X and Y. Okay, then you go like, looks like we can just do something like that, right? The negation of something is just that something originally. Is that okay? Does everybody understand? Double negation kind of cancels out. If you're not convinced, how are you going to say, okay, but I'm not convinced that double negation is just the original thing? What are you going to do to verify that double negation cancels out? You have seen that mechanism already. It's still on the projector. So what method are you going to use? Yes, a truth table. Very good. So just to illustrate that point one more time, because it is a very useful technique. So you just say, okay, x as a variable can only be true or false. And I want to know what happens to the negation of x. When x is false, when x is true. When x is false, not x is true, and then the negation of that is going to be false. When x is true, the negation of x is going to be false, but the negation of false is true. Ah, okay. So we have exactly the same value for all the rows. So now we have just established the equivalency between x and the double negation of x. So even though it may make sense in your head just by the semantics, the words, the meanings already, the double negation cancels out, now you have the actual table to show you, oh, they really are equivalent. So Boolean logic, Boolean expressions can be proven a lot of times using just a truth table. Okay, so with that said, so now I look at this whole thing and go like, okay, let me put extra parentheses that was not required, okay, around this part here. So what do you recognize in the part that is in parentheses? In other words, let me highlight the portion. What do you recognize? What is this? This is the negation of x and y. So this is x NAND y. Okay, that's kind of cool. So you take this out, okay, and we just go like, oh, okay, what is inside is just x NAND y. We're trying to negate the result of x NAND y. You go like, but how do we negate something? I think we just did that, right? If I scroll a little bit, We just did it. We know how to negate something. You have to basically take this whole thing and NAND itself. Okay? In other words, what we end up with is, if I need to express it, this is really clumsy compared to the circuit. So we have X NAND Y NAND itself. And I'm intentionally copy and pasting to emphasize that it really is the same thing on the right-hand side of this particular NAND. That will give you just regular AND. Okay? Now, so you guys are looking at this and go like, Tech, we trust you, and I think this is going to work. Don't do that, okay? Especially not in my classes. Just yesterday, in my CISP 440 class, my student said, well, last semester you said that there's a bug in your program and this truth table is wrong. I go like, no, I don't think that is the case. And sure enough, it was wrong, okay? So I do make mistakes, not intentionally, but I do. So it is always good to double check things. So what that means is, from your perspective, you probably want to double check that, in the truth table, that this is really the same thing. Okay, if I were to spell this out in a long way, and this is the way I do things, I do it in a structural way. Okay, so this is the outer NAND, and then the inner NAND is not X and Y, and that is repeated. Oh, okay, I need to put the parentheses. I'll take this out, put it here, and then copy and paste this on the other side of the outer double ampersand, double ampersand. So I would encourage you to do this. Okay, now does it mean that you have to turn it in and it's worth some points? No, but does it mean that it's going to help you understand the material better and develop the technique to do stuff like this? Yes. So you'll be the judge to decide whether you want to do this or not. So I want you to complete this truth table. I'll give you the template. You get to finish the whole thing if you choose to. Or in Mission Impossible, what was the phrase? If you so accept the mission or something like that. What was it exactly? I just, what? Mission Impossible, Tom Cruise. No, there's a very specific phrase in Mission Impossible. If you so choose to accept the mission, blah 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 blah. I think it's something along that line. Cannot remember. All right. So I will give you all the values of x and y, and you have to fill in the column corresponding to x and y. And this really kind of nasty thing, okay? I know it looks nasty, but it's not really as nasty as it looks. Because once you figure out one side, the other side is actually the same. So you just have to, kind of remember that. So this is kind of like my unofficial assignment to you, just so that you can get some practice of using a truth table. And I see that people are taking notes. Great. And I'm going to wait until I see that you guys are done copying, and then we'll move on. This is also getting recorded. So one trick with my lecture is, first check with me to make sure it's recording. And then you look at the time, and all you have to do is to jot it down. Oh, ungraded assignment at the time of 9:19 or so, and then go to the video, fast forward to the 19 minutes into the video recording, and bam, you get everything on the screen along with my annoying voice. But that's not going to work with many of your other classes if the professor is not recording the lectures. So it's always good to kind of have the habit of writing it down. All right. So with that said, shall we move on, or do you guys need more time to write this down? We're good? Okay. All right. So the next one is or. So we have x or y. Oh man, this looks kind of nasty. So we're going to look at this and it's kind of the same technique, but it's not exactly the same. So we're going to use double negation again, but this time I have to use something that you have not learned yet. It is called De Morgan's law. De Morgan's law looks at the negation of an or, and it says, oh, it really is the same thing as negating each thing inside the or, and then turn the or into an and. So the step from the second line to the third line is not something that I expect you to know already, okay? But it is one of those things, okay? But for those of you who are curious, okay, if you don't mind spending the time, you can use another truth table just to illustrate how De Morgan's law works. So this is the truth table for De Morgan's law itself, and this one is definitely optional because it is not exactly in the scope of this class, but if you want to kind of hone your skills in Boolean algebra as well as knowing how to use a truth table, this is another truth table you can try to complete. And once you complete it, you should see the column under the negation of the or is identical to the column that is under the and, but each item on the left and the right hand side are negated individually. Okay? So this is a De Morgan's law, kind of truth table. It is optional that you do this. But getting back to the conversion to NAND, so now I can go like this, go like, oh, okay, I can identify the first NAND, which is not X NAND not Y. I can recognize that because this is the negation of an and the things that we are NANDing would be not X, not Y. So now I'm left with, oh, but how do I negate X and how do I negate Y? Well, we actually learned that like way earlier because we concluded that, where is it? Here. So we concluded that not X is really just X NAND X. So now we can reapply that technique over here and say, oh, this part is really just X NAND X. And then the other part is just Y NAND Y. Oops. Yeah, come on. There we go. So now, I mean, yes, this is going to be one nasty expression for you to double check with a truth table. So, just do it once or twice is fine, okay? You don't have to do it for everything. But the main point is, oh, I just translated or, which is what you learned in Cisp 360, into this really rather obscure universal operator called NAND, which means I can make or out of transistors too. It's just it would just be like a little bit bigger because each NAND is going to take 4 transistors. This one will actually need 3 NAND gates, so that it would need a total of 12 transistors. But the point is, I can do this in hardware. Is that okay? So that's kind of the way I would teach you this class is bottom up, starting out with hardware devices, onto gates, and then onto something else. Alrighty, so that pretty much concludes the module that we were talking about, which is module 20281. So now we are moving on to the next module. So for those of you who want to, oh, I want to be able to read ahead of the class, you can just kind of go sequentially. So we got some labs, and then we got some videos to show you how to use the command line interface in Windows and also in Linux/Mac OS. So if you don't know how to use a CLI yet, watch that video. It is going to be helpful. All right. It is not only going to be useful for this class at ARC, it is also going to be helpful in, I think Ryan uses command line tools in CISP 400, and many UCs and CSUs also utilize CLI tools in their classes. So this is just going to be useful in general. All right, so we are now moving on to values, numbers, and bases. That's the next reading module. It talks about base conversion. It's a little bit long, because I tend to explain things in a certain way. I start with things that we already know, and then do the abstraction one step at a time until it becomes unrecognizable. It's like, what is this? Well, it started off with that you already know. Okay, so we'll go ahead and do that without reading my notes. Okay, if my lectures involve just reading my own notes, I will bore myself to death. I cannot do that, even if you guys ask me to. So what we'll do is we're going to use some examples that I have never used before, but the idea is still the same. Yes, that is a good question. Okay, so I like that question because I never thought of explaining that. Okay, so we'll take a look at, let's say let's see which one has the most parentheses. Yep. Let's take a look at this one. Okay, and I'm going to do it in Logisim just so that it's easy for you guys to see it, right? So let's go to Logisim. Let me launch Logisim first. Okay, so Logisim, there we go. All right. So in Logisim, because the focus is if we already have the NAND gate, how do we do the rest, right? So I'm going to cheat a little bit and not to construct my own NAND gate, and instead I'm going to use the NAND gate that comes with Logisim. So we'll pick out a NAND gate, just kind of slap it here. The default of a NAND gate is huge and it has 5 inputs. So the first thing I typically do is to change it to only 2 inputs and make it a little bit smaller, like so. And I'll document this too. So this is using, I'm just going to try to explain X and Y is the same thing as um, X NAND Y NAND X NAND Y. Okay, because I want to kind of make sure that when you watch this video, you know what it is about. So now the context is already here. So I'm going to need 2 input pins. Okay, the first input pin is corresponding to the variable X. The second input pin is going to be corresponding to the variable Y. And I need one output pin. So the output pin, I'm going to stash it over here. And it is labeled as what we want, okay, which is X and Y. So are we doing okay so far with just the general setup of the circuit? I haven't really talked about the inside connections yet. So we're good with the labeling of the input pin and the output pin and the purpose of the circuit. Yes? Okay, very good. So to make this circuit work, okay, I will need 2 of these. So I'm going to use a duplicate here and just stash this one over here. The first one is going to compute X NAND Y. Since this is already a NAND gate, that's pretty easy. X goes to one of the inputs, Y goes to the other input, and the output of this thing is going to be X NAND Y. Are we good with that? All right. So because this is already X NAND Y, and I want that thing to NAND itself, that's the job of the second NAND gate. So that means it goes to one of the inputs of the second NAND gate. It also goes to the other input of the other input of the same NAND gate, and then the output of this is because this is X NAND Y, so is this. So the output is X NAND Y NAND X NAND Y, which is what we want. I can claim this all day long, but you should not trust me, right? So I mean 0 and 0 is a 0. 0 and 1 is a 0. 1 and 0 is a 0. 1 and 1 is a 1. The circuit works. Is that okay? So I hope this answers your question of how to translate from the expression, which is here, into a circuit that looks like this. Yes, it is simpler as a circuit because I can refer to the same expression just by tapping the wire one more time. Yep. All right. That's an excellent question. All right. So we are, let me hide this, go back to my notes here, and we'll now talk about base conversion. So there are two things about base conversion that I will need to bring up first, and hopefully none of those presents a challenge to this class. The first one is, let's imagine that you're working at a fast food place and you need to, and the change is $10. Let's make it like $13 and 67 cents. Okay. So you're working at the counter of, say, McDonald's, and somebody just bought something that's worth $6.33, and as a result, and give you a $20 bill, the machine already calculates this is the change. So the question is, can you make that change using the least number of coins and dollar and bills, and not to give the customer 1,367 pennies? You can do that, but I think you may not be able to keep your job after that. So, so that's the question. Can you do this? Can you make that change? Now, I know this question is slightly biased because people who have not been in the United States for too long may have to struggle with this a little bit. And that has to do with the crazy denomination system of the US currency. For those of you who grew up here or have spent like 5 years or so in the United States already, we go like, I don't see why that is a problem because you're used to it already. You are you have been submerged in the poison for so long that you have developed immunity and not realize that you are actually submerged in poison. Okay, that's sort of how I would describe it. So so let's go ahead and check this out, and we'll do it in a very systematic way. So we're going to talk about, okay, so let's just say that if McDonald's in the cash register, they only keep track of $20 bills, $10 bills, $5 bills, $1 bills, because $2 bills can be confusing. And then in the coins, they have quarters, not half dollars, because once again, it is confusing because it's not common. Dimes, nickels, and pennies. I mean, just remembering the names of those coins is already an exercise. Okay. All right. So for in order to make a change for $13.67, do we need any $20 bills? None of those. One of those. None of those. Three of those. Two of those. Then you need one of those. Let me see. I have to keep track. One of those and then two of those. Okay. So if you're following this and you say, Tech, I can do this faster than you did, congratulations. Not only because you can make change, but because you already know base conversion. You're like, what? This has nothing to do with base conversion. There's no base 2 or base whatever in this whole thing. Just bear with me, okay? But do we have any questions about the mental process of calculating the number of coins and and bills in this little exercise? Are we good? Okay. So if you are kind of new to the US currency denomination, this might take you a little bit of time to understand because, okay, let me go back and explain why I think this is crazy. Let's find out the ratio between neighboring denomination. There are 5 pennies in a nickel. There are 2 nickels in a dime. There are 2.5 dimes in a quarter. There are 4 quarters in a dollar, and then there are 5 $1 bills in a $5 bill. And you might think, oh, we are repeating the pattern here. Look, there are 2 $5 bills in a $10 bill. So you would expect the next one to be a $25 bill because we want to repeat this pattern. But no, The next one is only by 2. And then we have the 2.5 to the $50 bill, and then back to the 2 for the $100 bill. Beyond that, I have no idea. I'm not rich enough to have that sort of bill in my wallet. But you can see how there's no repeating pattern whatsoever. And yet, you have mastered it. Okay, so think about that for a while. Okay, so you already know the basic idea of how to do this, you just have not realized it yet. Okay, so that's one. That's one thing I want to talk about. And then the other one is to look at a number and try to understand what it means. Okay, so this is all in base 10. Let's say we're looking at 51 point. I'm gonna pick a value that I can reuse later on. So we'll just go like 875. Okay, so this is a base 10 number. So I can rewrite this as 50 plus 1 plus zero point 0.8 plus 0.07, oops, plus 0.05. 005. There we go. Do we? Yes. Yeah, I said this is a base 10 number. Huh? Because it doesn't say anything other than, it doesn't say anything about the base. So by default, it is a base 10 number. All right. So do we have any questions about how I just broke this number into smaller terms? Okay. All right. And people will say, but this is elementary school stuff. It is. It really is. So now I can rewrite this as, oh, this is 5 times 10 plus 1 times 1 plus 8 times zero point 0.1 plus 7 times zero point 0.01 plus 5 times 0.001. Yes? Okay. It's like, okay, so I don't see where you're going. Well, we'll make this even more obscure. 5 times 10 to the power of 1, 1 times 10 to the power of 0, 8 times 10 to the power of what? Negative 1. Very good. Okay. And then we have 7 times 10 to the power of negative 2. And then we have 5 times 10 to the power of negative 3. Okay, so now we are starting to get into math stuff, right? So are we still feeling comfortable with the derivation? Okay. But are we seeing a pattern? What is the pattern? Yep. The power of 10 is just going from 1, 0, negative 1, negative 2, and then negative 3. But they're corresponding to the positions of the digits. In other words, this is our leftmost digit, and this is our rightmost digit. And you can see how the position of each digit is actually determining what power of 10 we should multiply to it. In simpler terms, it simply is saying that in a normal number, each digit is telling you the quantity of a power of the base. Okay, so you guys are looking at me, with a with an expression that is neutral. So I cannot tell whether you're understanding what I just said or you're puzzled by what I just said. You get it? Okay, very good. Okay, well, that's kind of important because now we are looking into how values are represented by numbers. In other words, fundamentally speaking, at least in this class, a value is different from a number because in most of your other classes, in math classes, for instance, those two terms are used interchangeably. But in this class, well, I make a distinction between those two. I'll give you another example to make this really clear. Um, what is the quantity that you're seeing here? 4. Okay, very good. But since Cantonese is my native tongue, I'm going to say that's the Cantonese word or character to represent this abstract quantity. Okay? And I'm assuming that most of you know another language, a language other than English. So now you can think in your head, or if you want to pronounce it out loud, that's fine too. Okay, so in the other language that you also know, how do you tell someone about this quantity? Okay, yes, Jaha. Okay, I'm pretty sure I'm butchering the language, but yeah. Okay, Farsi. Okay, Guado. Okay. Any Russian speaking students or students who know how to speak Russian? Okay. All right. So they're all different, but nonetheless, they are all representations of this quantity. Okay. So I want to make that distinction. A number is nothing more than a way to represent a quantity. The quantity is the abstract thing, but in order to communicate that abstract thing to somebody else, you need to use a word in natural languages, but you also need a number system in order to represent the value when we're dealing with computers. Is that okay? All right. So combining these two, okay, so I'm now switching back to my notes here. So I'm switching back to notes to kind of tell you how far we have gone through or how much we have gone through. So in this case, I'm using a slightly different value, but it's kind of the same. The individual digits are now abstracted. I will call this 6 here as D0. So what do you mean by D0? D subscript 0. The explanation of the notation is here. I know it's kind of hard to find it, but it's here. So I wrote here, we use the notation d subscript I to represent the digit that indicates the quantity of 10 raised to the power of I. So that's the general description of a digit. So D0 is right here for this, D0 is the 6 here because this particular 6 is telling us the number of 10 to the power of zeros. So to the left, we have D1. To the right, we have D negative 1, D negative 2, D negative 3. So I'll be getting a little bit more comfortable with the notation of using D with a subscript to designate a specific digit in a number. You good with that? Yep, go ahead. And also the position of the digit in the number. So those two correlate with each other. Where you find the digit is related to what power of the base you multiply to that digit. Yep. All right. And this is just a, kind of, it's not too important. The whole idea of this point here, the period in a decimal number, is just so that we know where is the line between digit 0 and digit negative 1. Because without that period, and in many other languages, they use a comma in this instead of a decimal point. But the whole idea of this particular punctuation mark is to serve as a separator from D0 and everything that is non-negative from D negative 1 and everything on the negative side. So that's the purpose of a decimal point. Is that okay? Huh? Without the decimal point, you cannot know, in the case where you have d negative 1, d negative 2, you would not know where the boundary is. So the purpose of the decimal point is to tell you on this side, from your perspective, on your left-hand side of the decimal point is D0. On the left of your decimal point, no, the other way around. On the left of the decimal point is D negative 1. Because without the decimal point, you would not know where D0 is. Is that okay? All right. So given that is the notation, so with a base 10 number, this is how we find the value of the base 10 number. This is how we know the value of represented by a base 10 number is to use a sigma notation, summation. where I is going from negative infinity as an integer to positive infinity as an integer, and then we each term we are adding to the sum is digit I times 10 to the power of I. So are we relating this sigma notation to the thing that we just talked about earlier? This is an abstraction of the concrete example that I gave you. Are we doing okay? All right. And you will find this pattern repeating itself quite a bit in this class. I will give you a concrete example that most people will think, oh, that's trivial, that's easy. And then in a few steps of abstraction, it turned into some notation people would look at and go like, what is that? Okay, because why do we do that in computer science? Why do we do abstraction? Because that's what a program is. A program is an abstraction of how something is done. And mathematics is all about abstraction too. In computer science, as much as some people do not want to believe this, computer science is a branch of applied math. How many people do not like that? But it really is. It depends on which branch of math. Okay, so applied math, okay. So by the time you get to CISP 440, which is discrete math, it is not the same kind of math that you do in calculus or linear algebra. It is a lot more related to actual programming. So that's also math. It is not actually, it's not programming. All right. So with this said, so now we go like, if I look at this expression here, which deals with base 10 numbers, if I want to use base 7 numbers, okay, which is a really awkward base to use, but I can, how can I come up with a way to describe how to get to the value of a number that is in base 7? Just looking at the screen here, okay, give it a shot. What do we need to do to change the sigma notation in order for this to deal with base 7? Change the 10 to a 7. As simple as that. Okay, so we'll give it a shot. Okay, so we're going to give this a shot. And in the mouse pad here, I will give you a number in base 7. So I'm going to randomly pick one. Okay, 3, 2, 4. And now I have to use, in parentheses 7 to emphasize that we are not looking at 324. We are looking at 324 as a base 7 number. Okay, all right. And if anyone is wondering, why would anyone use a base 7 number? The reason is, well, imagine you are in the world of SpongeBob. If you're not, I know this is also kind of cultural, but if you don't know what it is, you can just look it up, SpongeBob. So imagine you're in the world of SpongeBob and there's a whole village of drunk octopi. Okay? Yes, I know what octa means. It means 8. But in order to be drunk, the octopus need to have one tentacle holding onto a can of beer, and hence only 7 tentacles left to do the counting. And that's why it is base 7. So you can now draw a little SpongeBob on your notes just to remind you why base 7. It will help you remember things. Okay. Okay. But anyway, 3, 2, 4 in base 7. But what value is it actually representing? So now you have to say, okay, what is the 3 telling me, and what is the 4 telling me, and what is the 2 telling me, and what is the 4 telling me? So now you go back to what I said a little bit earlier. Each digit of a number is telling you the quantity of of a specific power of the base. Okay, so immediately we go like, oh, okay, I know how to kind of format this in a certain way. 3 is a quantity of something, 2 is a quantity of something, 4 is a quantity of something. A quantity of what? Well, if you recall what I just said, like 30 seconds ago, it is the quantity of the base raised to a specific power. So since this is in base 7, you go like, oh, okay, fine. It's base 7 raised to the power of something, base 7 raised to the power of something, 4 times 7 to the base raised to the power of something. So now the next question is, what power are we talking about? What do you think? Which one of these out of 3, 2, 4, which one is my D0? Using the same convention as base 10 numbers. Yes, the 4. Very good. Good job. So the 4 is my digit 0. So that means 4 is telling me the number of 7 to the power of 0. Do you think you can backfill this one? This D of 1. Very good. And this is D of 2. And the last thing I need to do is to add all of them together. Done. Okay, so let's go ahead and actually finish this calculation. So this is 3 times 49, because 7 squared is 49. This is 2 times 7, because 7 to the power of 1 is just 7 itself. And this is really just 4 times 1, because 7 to the power of 0 is 1. So now this is 147 plus 14 plus 4. And that would be 147 plus 18, which is 165, I think. 165 in decimal. Is that okay? Are we good? All right. So now you know how to read numbers in that village of drunk octopi. Any questions? Or you can now communicate with the heptapod from, is it Arrival, the sci-fi movie? The heptapods, they are the aliens with 7 limbs. Yeah. Yes, I spent too much time watching TVs and SpongeBob. All right. Are we doing good so far? So at this point, we have only talked about these kind of really odd bases. So now the question is, can we generalize that summation thing so they can deal with any base? The answer is yes. Just change the 10 to a B, where B represents the base, and now we have a generalization of how to read a number. B is the base, D is an array of the digits, I is the position of the digit itself, and V is the value represented by a particular number in a specific base. We good so far? All right. So next question is, okay, tackle enough of the absurdity of this class. So it's time to move on to something a little bit more practical, like binary numbers. Okay. So now the question is, do we know about this particular binary number and what it is representing? Oops, 2. There we go. All right. So I'm not going to show you the long form anymore because that's going to take a while. So I will tell you what I do in my head, and except it's a little bit more spelled out. So this is a plus 4, no 2, there's only a 1, no half, there is a quarter, and there's also an eighth. I can do this because I've done this many, many times. So now what do we have? We have what, 13.375, I think. Let me double check. Yeah, it is 13.375. All right. But the process is really the same. If you want to spell this out, so this is another unassigned, if this is another ungraded assignment that you can do for yourself, is go like, okay, how do I do this using the same longer process in order to figure out that 1101.011 in base 2 is representing the same value as what we see as in decimal 13.375. Okay. You can also use a random generator. Okay. You'll give yourself a binary number and try to convert it into the decimal representation. Are we doing okay so far? Okay. I'm just looking at the watch just to kind of make sure I have time to cover the topics that I want to cover. What about the other way around? Okay, that's the harder way, which is if I give you a value in base 10, because we can understand base 10 numbers really kind of right away, and I want to convert it back into a specific base that is not base 10, how do we go about doing it? In other words, that's the currency thing, okay? So how do we reverse that process? So we'll start with um, the one that is 51.875. We'll start with this one, and we will try to convert it to blah, blah, blah in base 2. Okay, because base 2 is actually one of the easiest bases to deal with. Okay, so imagine this is currency. Okay, this is $51, 87.5 cents. Okay, that's the quantity that I want to specify. So now imagine that you are in my ideal country where the currency is like this. Okay, so you will have $8 bills or eighth coins. You have quarter coins. You have half coins. You have $1 bills, $2 bills, $4 bills, $8 bills, $16 bills. What do you think is the next one? 32 and then 64. Very good. So those are the denominations in this particular country. You go like, that's really awkward. I cannot see why this is awkward when you can say, but the American denomination makes sense to me. This does not make sense at all. This makes perfect sense. Why? What is the ratio between the denominations? Everything is just double or half, depending on which way you look. Yeah, this is very systematic. You know what the next denomination is going to be. So, given this is the denomination and the amount that I need to make up is $51.87.5. So now we try to fill in these things. Like, do we need a 64? Nope. Do we need a 32? How many of a 32 do we need? Just one. So as it turns out, if you do it systematically, it's either a 0 or 1. You don't need division. All you need is comparison. If the remaining amount is greater than or equal to the denomination that you're considering, you need 1. If it is less than, you need 0. So it's 1 or 0. There's no division involved. Cool. So, but I do have to keep track of what is the leftover amount. So 51 minus 32 is what, 19.875? Yep, go ahead. Yes, it only involves comparison because this is base 2. Yep. In any other base, you would need division and mod. All right, so what about 16? Do we need a 16? Yeah, we're gonna need a 16, and we'll have 3.875 left. Do we need an 8? Nope. Do we need a 4? Nope. We're gonna need a 2, at which point we're gonna have 1.875 left. Then we're gonna need one of the 1 to take care of the 1s. Then we have 0.875 left. Do we need a half? Yep. And then after that we have 3.75. We need a quarter so that we have 0.125 left. And then we need a 1 to take care of the remaining portion. And then after that, we have nothing left. That's base conversion right there. Is this related to the way you make change in American currency? It's not. It really is the same thing, except this is easier. Because in American currency, sometimes you have to use division. Like 81 cents. Okay, so other than counting with your finger the number of quarters, the easiest way is to say, okay, 81 cents divided by a quarter is 3. So it involves division. This does not involve division at all. It's just comparison, subtraction, comparison, subtraction, comparison. Is that okay? Yep, go ahead. Well, that is a very good question. So the reason why we choose base 2 is not so much because of division or not. It has to do with um, transistors in a circuit, especially in an integrated circuit. They're not perfect. In other words, we cannot make the transistors all identical. They're going to have some variances. Okay. So if you rely only on whether the voltage is exceeding a threshold or below a threshold, that is easy to do, because it doesn't depend on the precision of the transistors being exactly the same and all behave the same. So that's why we use base 2, because we just want to rely on, is the voltage at a certain point above a threshold, or is it below a certain threshold? And it's relatively easy to manufacture transistors on a integrated circuit that has enough consistency so that it works as a whole if we only care about whether the voltage is above or below two different thresholds. As opposed to, oh, we want to divide it into like 4 different levels, then it gets a little bit harder. 8 levels, even harder, and so on. So that's the advantage of binary digital circuits as opposed to anything else, is it's harder for those things to stop working because you have a fairly generous um, range of operation in terms of the transistors. So that's a very good question. Um, so now we're going to move on to the general equation to figure out the digits, and we're going to try that out a little bit. Also, this is the equation, okay? So this is the equation that will give you d of I if you specify v, b, and I. So what are those things? What is v and what is b and what is I and what is d of I? Well, if you're having those questions, you might want to read the module also, okay? Because those are all explained. But I'm going to explain it here. V is the value that is being represented. B is the base that you want to use. I is the digit, the individual digit that you want to figure out. And then D of I is really just the value of digit I. All right. So all of that is actually explained in the notes itself. So I would say it is pretty important to read the notes just to make sure that you get everything from the notes, because that is how I make the exams. Okay, I make the exams based on the assumption that you have read and understood the modules as well as taken notes in class. That defines the scope of what I can possibly ask in an exam. All right. So how do we test this? So what we'll do is since Tech is absolutely lazy, so now we're going to use some of the previous example, okay? So we're going to use the base 7 example, and we say, okay, V, the value that we want to represent is 165. The base that we're dealing with is 7, because that was what we were dealing with. And I is 2, well, let's make it 1. So we are trying to figure out what is digit 1 of the base 7 representation of 165. Is that okay? So now we plug in all the things with one little caveat, because what is this thing here? It looks like a square bracket, but it's missing the top of the square bracket. Only the floor of the square bracket remains. It is called the floor operator. So let me first explain what is the floor operator. If you're taking the floor of a value x, then it becomes the largest integer that is less than or equal to x. So let's go through a few examples. What is the floor of 2.7? What is the largest integer that is less than or equal to 2.7? 2. That is correct. Okay, that's just 2. All right. Oops. What is the floor of 2.1? It is also 2. Okay, so floor is not rounding for sure, but it is kind of related to rounding. We'll see that later. What is the floor of negative 2.2? Aha, this one is a little tricky. So don't go by your intuition, go by the definition. Negative 3, that is correct. It's not negative 2 because negative 3 is the largest integer. That is, the most important part is less than or equal to 2.2 in this case, negative 2.2. Negative 2 is greater than negative 2.2. Negative 3 is less than negative 2.2. So it is important to make that distinction. All right. So now that we know what a floor is, let's plug in the numbers, right? So in order to figure out what is D1, in this case, we have to perform the floor operation of V, which is 165, divided by 7 raised to the power of 1, and then take the mod 7 of that whole thing. All right, so this is going to be, let's see. So this is going to be the floor of, it's 20, okay, 14, 2, 5, 3 point, blah, blah, blah. Okay, because the blah, blah, blah is not important, but I'm just going to stash it here. All right. So this is boiling down to the floor. It's boiling down to 23 mod 7. So what is 23 mod 7? What is mod? Do you remember mod from CISP 360, or was that mentioned in CISP 360? Okay, so what is 23 mod 7? 2. That is correct, because it is the remainder of 23 divided by 7, so it is a 2. So was digit 1 a 2 when I was using the base 7 example? Let's check. Yep, there we have it. That's the 2. Okay. It also works on negative power. Okay, so we'll go through another example. Okay, so we'll use the binary example this time. So the value being represented is 51.7875. So Control C and then Control whoop, B over here. The base is 2 because it's binary, and I'm gonna use negative 1 in this case. So we wanted to figure out what is digit negative 1 of the binary representation of what we know as 51.875 in base 2. Well, okay, it was redundant because I said binary and base 2 at the same time. If you caught that means your listening skill is really up there. How many people caught that was being redundant? Sort of. Okay, very good. And these are all the soft skills that will help you in your career. In the long run, these are all the important stuff. It's not so much just the technical stuff, the soft skills are also extremely important. All right, so let's go through the math here. D of negative 1. So I'm putting negative 1 in bracket just so that it is clear that this is subscript. And this is going to be the floor of 51.875 divided by 2 to the power of negative 1, the whole thing mod 2, because 2 is the base. And just to be really clear, the whole thing is in the denominator of the division. So we'll do this step by step. This is 51.875 divided by 1/2 or 0.5. Okay. And dividing by half is the same as multiplying by 2. So this would be 103.75, I think. Okay, let me double check. So mental math. So this would be 1.75 and 51 times 2 is 102 plus the 1 from the carry. So I think that is correct. Does anyone want to check? I can do it. I can use it using a tool. And you guys go like, Tech, do you use a command line tool to do everything? Yeah, just about. That was 51.875 times 2. Yep, okay. I'm now convinced. All right. So the floor of that is just 103, and we want to do a mod 2. That's easy, right? We got our one back. But which one are we getting back? There were 3 ones to the right-hand side of the decimal point. So this is -1. So this is the digit that is immediately on the right-hand side of the decimal point. All right. So we have covered a lot of stuff today, and I still have time left. What have we covered today? So it's always good to have a summary of what we learned in a day, just so that when you review the material, it gives you a catalog. Okay, if you need to find out, okay, I need to find out, or I need to remember, what base conversion is about. It's good to have a little catalog, in your own notes. So we covered how to convert, not convert, but how to make and or not gates out of just a NAND gate. That's the beginning of the lecture. We talked about base conversion, which started off as how do we read a number, okay? And then we generalize that to the general, sigma notation. So when you are given a number in a specific base, then you can find out what value the number is representing. We also talk about base conversion, and I started off with the example of making change. If you can make change, which is using irregular intervals between the denomination, then you already know about base conversion because you already know, oh, okay, we start with a larger denomination, and then we just have to use division and subtraction, in order to get down to the lower denominations. And then we talk about how to do it in a very systematic way, using the equation that is expressed here. And then we went through a few examples, and then we talked about SpongeBob, we talked about Arrival, the movie, and I think that pretty much sums up today's lecture. So is everything okay? Are the concepts sinking in? So it's sinking in today. Are you guys all taking notes? You don't have to answer the question. If anyone is not taking notes, the question is, do you still remember what we talked about today, a week from today, 2 weeks from today, and so on? Okay, because that really is the question. Okay, I'm not questioning, are you understanding the material as you are here listening to me? Okay, the question is, can you retain that information and be able to retrieve that information a few weeks down the line? And taking notes is the way to do it. Okay, so your notes, the notes that you're taking, will also eventually become your study guide. I do not provide any study guide to my students because study guide is individual. What works for me, what is a good organization for me, can be a disaster for you because we do not think the same way, we do not organize the same way, we do not look up things the same way. So that means you have to be the one creating and maintaining your study guide along the way. It is not something that you do like 2 days before an exam. It is something that is ongoing. It would be a good way to use part of the 2 hours per hour of lecture in the classroom. So you can now kind of put create a checklist. Okay, how am I supposed to be spending the 2 hours of outside time per hour of lecture time in the classroom. Make a little checklist so you can remind yourself what you need to do when you are not in the classroom. Review the notes, okay? Review or preview what is going to be in the next lecture, okay? Revise my notes. In other words, you go through your own notes that you were taking in the class. You go like, oh, okay, now I have an insight that I didn't have when I was in the lecture. Write it down, okay? Because the insight would be one of those things that I cannot record in the lecture recording because it is in your thoughts, not mine, okay? Um, Maintaining your study guide, another thing, right? You can also condense your notes. In other words, okay, we have gone through a lot of notations and a lot of equations. I'm going to stay organized. I'm going to put all of these over here, all of these over here, and so on. But some people may say, but Tech, everything is in your modules and I can just print them out. Yes, you can. But can you locate the equations quickly? I can tell you one thing that is embarrassing. Even I cannot do it because even though I wrote all of this stuff here, I cannot remember where I stashed my stuff. Okay. So that means you need organization because we will have a lot of notations in this class, a lot of equations in this class. Now, do you really want to remember all the rationale, like how did we derive this and whatnot? Maybe, maybe not. That is up to you. Okay. But knowing where to find the finished product, like, oh, this notation means this. This equation helps me to figure this out when I'm given those. Those are the important things that you need to organize. So kind of keep that in mind. Different people organize differently. Some people like to do it all digitally on the computer. Cool. Some people like to write notes. Some people like pictures. Some people like graphs. It is entirely up to you. There's no best way to take notes that works for everybody. Is that okay? Since I still got 3 more minutes and I don't want to give you refund for those 3 minutes, I will bring up something that might be of interest to some of you. There is a book and a whole enterprise, thriving on this thing. Um, I'm just gonna look it up. Taking notes as second brain. Okay, I don't need the AI to tell me that. I think this is actually a book itself. Um, Basically, if you think about your brain, it is amazingly powerful. It can do a lot of things, but remembering details is not one of those. So taking notes is kind of like developing quote unquote a second brain. I mean, they compare that to having a second brain, but it's really kind of just an analogy. But the importance of taking notes is kind of, it's universal. Okay, there are a lot of people who have done a lot of research. Um, how many people? You don't have to answer this question. So typing versus writing also makes a difference. So it's a trade-off. If you're typing and you know how to do markdown and all the really cool stuff, and you can have equations and actual mathematical symbols and really fast, that can be helpful because you can capture almost everything that I'm talking about. And since the lecture is recorded anyway, you can always go back and kind of look at all the details. But the difference between writing and typing is because most people cannot write very fast. And a lot of professors do not give you extra time and ask you, okay, do you need extra time to take notes? So you're always kind of scrambling. So the correct way, well, I shouldn't say correct, but one way to do this is your brain is trying to absorb all the information and then try to condense it in a representation that you can actually write down in time. That process is helping you, one, to understand what the professor is saying, and two, it establishes additional pathway in your brain to recall that piece of information. Listening is one pathway. Writing about it is a second pathway. After class, you talk to another classmate and you try to explain the same concept to your classmate. Speaking about something, talking is another pathway. And hopefully you guys will eventually read my modules. That's the fourth pathway. So reading, listening, writing, and talking about it, those are all different pathways. And each one will help you build additional linkages and connections between the concepts. That makes it more efficient for you to retrieve the information and the concepts in an assessment or when you need to apply that even in your career. So I just want to kind of explain the uh, psychology behind how your brain make connections between the concepts and how things start to become permanent or long-term memory, as opposed to okay, I understand everything you're talking about. An hour later, you go like, I have no idea what Tech just talked about, and I'm the prime example. Many times, my students, such as yourselves, would ask me, Tech, could you just repeat the sentence? I would go like, I cannot remember what I just said 20 seconds ago. Because once the words come out, it's like, it's gone. It's not in my head anymore. So I just want to emphasize that. Okay. Even when I talk, I cannot remember what I just said most of the time. But I still remember the example of SpongeBob because that kind of stood out. All right. Well, the lecture is over. The lab is not visible yet. I'm going to make it visible. There we go. It is visible now, and you are going to need the access code. The access code is Nandroid because this particular lab has to do with, guess what? The NAND gate. So Nandroid is the access code. It will require your circuit file from the previous lab. If you did not get a perfect score, meaning your NAND 2 implementation is not working entirely, I can give you mine as a starting point. So let me just do that. I will put it into the announcements. Okay, there we go. And Canvas would actually take a few spaces as content. All right, so NAND. Now I have to remember which one is mine and which one is my students. Okay, better double check that first. Nope, that's the wrong one. So it's the one without the two. Okay, the one without the two. That will be this one. There we go. And send it away. All right. So I think you have everything that you need to start on the lab. I'm also putting concepts related to Logisim into the TA, into the GPA TA. So if you want to know, okay, how do I use a splitter, and ask the TA, it would actually be able to answer that. So I'm trying to put everything related to this class into the custom GPT. If you have not tried it out, okay, you might want to just kind of give it a try when you have time. Um, I am somewhat impressed by what it can do. All right, so I will stop the recording, get it uploaded, and go